Hello students, have you ever tried solving a system of equations and wondered what actually decides if the solution is unique, impossible, or infinite? The answer often lies in something called the determinant. A determinant is simply a unique number, real or complex, associated with every square matrix. Square means the number of rows equals the number of columns. This single number tells us a lot about the matrix. It can help us decide if the matrix has an inverse and whether a system of linear equations will have a unique solution. If capital A is a square matrix of order n written as A equals bracket A sub ij bracket close, then its determinant is written as mod A or det of A or the Greek letter delta. But remember, determinants are defined only for square matrices. You cannot take the determinant of a rectangular matrix. For example, if A equals the 2 by 2 matrix with elements A, B in the first row and C, D in the second row, then the determinant is mod A equals A times D minus B times C. In short, determinants give us a compact way to assess properties of matrices that have big implications in algebra, geometry, and beyond. Let's start small. For a 1 by 1 matrix, say A equals bracket a bracket, the determinant is simply mod A equals A. For a 2 by 2 matrix, say A equals double square bracket A1, A2, A21, A22 double square bracket close, the determinant is mod A equals A11 times A22 minus A12 times A21. This value even has a geometric meaning. It represents a signed area which appears in topics like transformations and analytic geometry. Example 1. If A equals the matrix double square bracket 2, 4, minus 1 to double square bracket close, then mod A equals 2 times 2 minus 4 times minus 1, which equals 4 plus 4, giving 8. Example 2. If A equals double square bracket x, x plus 1, x minus 1, x double square bracket close, then mod A equals x times x minus open bracket x plus 1 close bracket times open bracket x minus 1 close bracket. That is x squared minus open bracket x squared minus 1 close bracket, which simplifies to 1. So, even for small matrices, determinants have clear patterns and powerful interpretations. Now, let's step up to a 3 by 3 matrix. Suppose A equals double square bracket A1, A2, A3, A21, A22, A23, A31, A32, A33 double square bracket close. We can compute its determinant using cofactor expansion. If we expand along the first row, the formula is mod A equals A11 into open bracket A22 times A33 minus A23 times A32 close bracket minus A12 into open bracket A21 times A33 minus A23 times A31 close bracket plus A13 into open bracket A21 times A32 minus A22 times A31 close bracket. The beauty here is you can expand along any row or column and you will always get the same answer. In practice, you should pick the row or column with more zeros to save time. Example, let's take A equals double square bracket 1, 2, 4, minus 1, 3, 0, 4, 1, 0 double square bracket close and expand along the third column. The result is mod A equals 4 into open bracket minus 1 minus 12 close bracket, which equals minus 52. Cofactor expansion is like peeling the matrix layer by layer, breaking it into simpler determinants. Determinants have some very handy properties. First, if A equals K times B, where K is a scalar and A and B are n by n matrices, then mod A equals K to the power n times mod B. Second, for the product of two square matrices of the same order, mod of A equals mod A times mod B. Third, determinants don't change when you take the transpose, that is, mod of A transpose equals mod A. Also, a matrix is called singular if its determinant is 0 and non-singular if its determinant is not 0. Finally, in geometry, the area of a triangle with vertices x1, y1, x2, y2, and x3, y3 is half times mod x1 times open bracket y2 minus y3 close bracket plus x2 times open bracket y3 minus y1 close bracket plus x3 times open bracket y1 minus y2 close bracket. This triangle area formula can actually be written neatly as a determinant, showing the deep connection between algebra and geometry. Let's apply our knowledge to a trigonometric example. Suppose A equals double square bracket 0 sine alpha minus cosine alpha minus sine alpha 0 sine alpha cosine alpha minus sine alpha 0 double square bracket close. Expanding along the first row, we get mod A equals 0 minus sine alpha times open bracket 0 minus sine alpha times cosine alpha close bracket minus cosine alpha times open bracket sine alpha minus 0 close bracket. That's equal to sine alpha times cosine alpha minus cosine alpha times sine squared alpha. Look closely, these terms cancel out, giving 0. This shows that when a matrix has symmetry, patterns, or zeros in strategic places, the computation becomes much simpler. Sometimes, even before expanding, you can predict the determinant will be 0. Determinants are more than just a calculation tool, they're a decision-making tool in solving systems of equations. If you have a system Ax equals B, where A is the coefficient matrix, then if mod A is not equal to 0, the system has a unique solution, and that solution is x equals A inverse times B. If mod A equals 0 and adjoint of A times B is not equal to 0, the system is inconsistent, it has no solution. If mod A equals 0 and adjoint of A times B equals 0, the system may be consistent or inconsistent, it could have infinitely many solutions or none. This flow of conditions helps us quickly determine whether solving the system is worth attempting or not. So, to wrap up, determinants take a square matrix and boil it down to a single number, revealing critical information about solutions, invertibility, and transformations. We've seen how to compute them for 1x1, 2x2, and 3x3 matrices, learned a cofactor expansion method, and explored properties that make calculations efficient. We've also looked at how determinants are applied from calculating triangle areas to solving linear systems. Always remember, if mod A is not equal to 0, the inverse of A exists, and the system Ax equals B will have a guaranteed unique solution. And that's the foundation of how we compute determinants and understand their role. In the next video, we'll dive deeper into using determinants for solving systems via Cramer's rule.